So moving on, we're fortunate to have a presentation tonight regarding fracking, and we're very fortunate to have a presenter who's quite accomplished, Dr. David Yoxtheimer, and I think that's how you pronounce the name, Dave?
Yes.
Okay, and I read your bio, and it's quite impressive. You're a Ph.D. as a hydrologist and an earth scientist and a geoscience professor, and you're part of the Penn State University's Marcellus Center for Outreach and Research, and you also teach at Penn State, and notably you're on Governor Wolf's Pennsylvania Department of Environmental Protection Oil and Gas Technical Advisory Board, and I guess you're the chairperson, if I'm correct.
That is correct.
We thank you for coming, and we're all ears.
All right. Well, thank you for having me. I apologize I couldn't make it to lovely Narrowsburg tonight. So hopefully I can convey the information this way. I assume you can see my screen?
Yes. Yes.
Okay, great. Okay, well, I tried to keep it kind of relatively concise. So hopefully we'll have a little bit of Q&A time on the back side of this. But just moving on to the first slide here, a little bit of context. This is a map of the Marcellus Shale. As you can see, it does extend into the Delaware River Basin, especially up in the Wayne County area of Pennsylvania, and then up into the southern tier of New York. So, you know, most of the Marcellus that's prospective for drilling is, you know, out of the Delaware Basin. But, you know, there is a little bit of area there, especially in, you know, when we think about it from Pennsylvania perspective, in Wayne County, where the shale would be at depths of around 5 to maybe 7,000 feet below the ground surface. You know, it is a very large shale gas basin, about 500 trillion cubic feet of gas that can be recovered with today's technology. So, you know, from an energy perspective, it is, you know, an important source of energy, but obviously it does have, you know, potential environmental impacts that we need to minimize. So beneath that, we've got the Utica / Point Pleasant shale, which actually even may have more natural gas and natural gas liquids such as ethane, propane, butane, even oil in it. Those liquids are mostly, you know, in western Pennsylvania and into Ohio. Nobody's really drilled into the Utica beyond Tioga County. Would be about the furthest east it's been drilled. So whether it would be even potentially prospective further to the east is sort of an unknown at this point. But it's on the order of 5,000 feet below the Marcellus in northeastern Pennsylvania. So quite deep, and possibly any hydrocarbons in it have been geologically destroyed a long time ago. This map will kind of go through a time series of where wells have been drilled up through the end of 2019. So generally this, you know, map should be pretty contemporary. You can see up in Wayne County, approximately maybe up to 4 wells were drilled within the Delaware Basin. Those were test wells where early on in 2009-10 timeframe, companies were exploring the potential for the Marcellus Shale there, but then soon thereafter, you know, the ability to drill in the Delaware River Basin was taken off the table. But we have about 13,000 wells drilled in Pennsylvania in both the Marcellus and Utica. There's a couple other formations up what are collectively known as Upper Devonian shales, where there's been some limited drilling, but the Marcellus by far is the most prolific as far as production goes, and then you do have some Utica production occurring in Pennsylvania. If we just take a look at current shale gas production, we're near 25 trillion cubic feet per year across the U.S. And if you look out into the future, out to year 2050, the Energy Information Administration, which is part of the Department of Energy, expects we might see another roughly 8 trillion cubic feet. So roughly 33 trillion cubic feet of shale gas could be online by 2015, with the Marcellus and Utica providing nearly 50% of that production. So again, from an energy standpoint, these are very, strategic sources of energy. But again, obviously there are, potential environmental impacts. So we need to consider that. And that's what we're going to kind of focus on here in the latter part of the talk. Just to get everybody on the same page. When we think about the different water management phases, that's really kind of what we're talking about here today. One, you'd have the water acquisition. Where's the water coming from? In this part of the world, it's mostly surface water, a little bit of groundwater. You're bringing it on site. You're mixing that water with the various additives during the hydraulic fracturing process to optimize the overall process of fracturing to enhance production. You're injecting the fluids down into the shale to open up fractures. And then once the hydraulic fracturing process is complete, you're going to start to produce gas, but along with the gas, you're going to have some of those fluids that were injected down into the shale come back up, along with naturally occurring brines that exist down in the shale that were in essence originally deposited and trapped in the shale, which is roughly 390 million years old if we think about the Marcellus, and about 420 million years old if we think about the Utica shale. And so those fluids that come back out of the well are going to tend to have residual concentrations with the additives that were used for hydraulic fracturing, but they also bring out a host of contaminants from deep in the earth, naturally occurring salts, metals like barium and strontium. You can have naturally occurring radioactive materials, radium, radon, things of that sort. And so collectively, these are not, even though they're naturally occurring, doesn't mean they couldn't be harmful to us. So that's why this waste stream needs to be carefully managed. There's a whole host of regulations at the state level to ensure that these fluids are to be handled properly to minimize environmental impacts, but obviously regulations are only as good as the associated enforcement. And I'll go into detail as to how the industry is managing these fluids in just a little bit. Just want to kind of give a high level view of the various water management stages of shale energy development. When we think about the amount of water being used this is from the Susquehanna Basin, just to give you a little bit of perspective. The gas industry is using about 24 million gallons per day. That's what the MGD stands for, which is a little less than 10% of the approximately 263 million gallons per day that are withdrawn again on a daily basis here in the Susquehanna Basin alone. Roughly, a third of that goes for power generation, cooling water. Another third is public water supply. And then, the third leading withdrawal is for the natural gas industry. And then there's a host of other water uses: agricultural, manufacturing, recreation, pipeline mining, and a variety of other sectors. So just to kind of put a big picture on the water volumes being withdrawn on a daily basis. Within the Susquehanna Basin, the industry is again, this is a study from 2020, but it only goes up through 2018, and you can see that there was a pretty significant drop off from roughly 2017 into 18, where at one point the industry was withdrawing up to 14 million gallons per day, and then it dropped down to around 7 to 8 million gallons per day. A typical well will use roughly 1 to 2 million gallons per 1,000 feet of lateral. So again, these are horizontal wells that are being drilled into the shale. Depending on how long the well is, dictates how much water is used per well. But it's pretty common to see somewhere in the neighborhood of 10 million gallons per day, maybe upwards of, 10 million gallons per well, maybe up to 20 million gallons per well for some of the longer laterals out there. In all of Pennsylvania, surface water makes up about 90% of the water, fresh water being used out there. And then public sources and groundwater make up the balance, about 10% of the water being withdrawn. So it's mostly a surface water withdrawal is where the fresh water is being generated from. We have been seeing a significant increase in the produced fluids, the fluids that come back after the well has been fractured, anywhere from less than 10% to upwards of 90% of the fluids can be added into the fracturing fluid mixture. And as a whole, we're seeing on the order of 90% of those return fluids, those produced fluids, being recycled. And again, I'll get into some more detail as we dive deeper in on that. So this looks again up through 2018 within the Susquehanna Basin. There is on the order of approaching 5,000 wells, shale gas wells in the Susquehanna Basin, and the average water use per well on the left hand axis there is between 10 to 12 million gallons now per well. You can see that number's increased over the last decade. Again, as the horizontal sections or the laterals of these wells get longer and longer, the amount of water to fracture the length of the well is commensurately greater. So when we think about some of the produced water management options, and again, produced water is the fluids that return after the well's been fractured. So this is coming out along with the natural gas. It's got high total dissolved solids. Most of that is the salinity. So the salinity may approach, being 10 times saltier than the oceans. So on the order of, in excess of 300,000 milligrams per liter of total dissolved solids. Again, the majority of that being salinity. Again, there's barium, there's strontium, there's radionuclides in there. So again, these fluids need to be properly managed. So really we see 4 different pathways for that waste stream. Basically directly reusing the fluids, collecting them, and then using them to fracture the next well. We do see mobile treatment systems where they might keep the water in the field, but they might treat the water and then blend it with fresh water and send it back down the next well that's being fractured. There are centralized treatment facilities where the fluids may be transported to a specialized treatment facility designed specifically for produced fluids, treated and then brought out back to the well sites. But now you're transporting these fluids. And so now you're increasing the risk of, an accident or a spill on the roadway. Obviously there's, diesel emissions. These fluids are being trucked from point to point. And there's costs associated with that. So collectively, the industry's gone more toward trying to reuse the fluids in the field, which keeps, the risks down and the carbon footprint down. Ultimately, if the fluids need to be permanently disposed of, there are disposal wells, although we have a limited number, roughly 12 disposal wells that are permitted and only roughly 6 that are operating in Pennsylvania. So there's not a lot of disposal well capacity in Pennsylvania. So the about 3/4 of those fluids that aren't being reused are being disposed of in injection wells in Ohio. So again, a lot of trucking associated with that, a lot of cost associated with that, and a greater carbon footprint associated with that. But those are, in essence, the 4 major pathways for these fluids to be either recycled, treated and recycled, or disposed of. There are a couple plants in Pennsylvania, one in Williamsport and one up near Towanda, that actually that have advanced treatment, so they can desalinate the fluids, remove the salts, meet total dissolved solids discharge limitations set by the state, and then be discharged into a receiving surface water. So there's a couple of facilities that do have the capability to do that. It doesn't make up a large fraction of how the fluids are being managed, but that is an option out there if the fluids can be properly treated. And by properly treated, basically you have to reduce the total dissolved solids to a concentration of less than 500 milligrams per liter, which is consistent with drinking water standards, basically a secondary drinking water standard set by the EPA. So if we look at how the fluids were managed across Pennsylvania, these produced fluids produced 69 million barrels in 2021. The 2022 numbers just aren't out yet, so I can't share that with you, but they shouldn't really be a whole lot different than what you're seeing here. To put that in perspective, for every million cubic feet of gas you're producing, you're going to get about 9 barrels of fluids. In oil field, gas field jargon, there's 42 gallons in a barrel. So you're looking at about 400 gallons of brine for every million cubic feet of gas produced. And Pennsylvania produced 7.7 trillion cubic feet in 2021. And I think it's just going to be a little bit more than that in 2022, but not a whole lot more. So again, you'll see similar numbers coming out here in the next month or so. The recycling rate, so capturing these fluids and reusing them to fracture a well, was about 89%. So 61.3 million barrels out of 69 million barrels were recycled. Nearly 60% of those fluids were recycled in the field. Roughly 35% were taken to these centralized treatment facilities. So that involves trucking to the facility and then back out. And then about 8% of the fluids were reused at well pads outside of Pennsylvania, so namely West Virginia or Ohio. And then roughly almost 44 million barrels of fluids were, I'm sorry, that should be 4.37, sorry about that, million barrels of fluids were handled by a disposal well. So that represents about 6% of the fluid. So again, 75% of those fluids were sent to Ohio, about 25% were sent down disposal wells in Pennsylvania, and just a little bit less than 1% was sent to West Virginia. All right, so what I thought I'd do to break this down is to look at the different phases of shale gas development, and then look at some of the issues and possible solutions. These are existing solutions. These aren't something I just came up with today. These are either by regulation or sort of standard industry practices. But when we think about the drilling, you're looking at an aerial photo of a drilling rig. A lot of the drilling's happening in rural areas, forested areas of Pennsylvania. So there's certainly, land and habitat disturbance concerns, forest fragmentation. And so this is where, between the regulators and the industry, well site selection really matters. Stay away from, sensitive areas, whether it's wetlands, and there are setback distances and things like that are in the regulations. And there are some technologies that can be used to minimize the surface footprint. Maybe a lot of the well pads you see may be on the order of 5 to 10 acres. That area can be shrunk down, that disturbance, if you have the right kinds of technologies. Another issue would be diesel emissions. You do see a lot of rigs have been running on diesel. You are starting to see a turnover to using natural gas powered rigs, even electric powered rigs that use generators that run on natural gas. So there are some options there as far as reducing air emissions. You have potential for surface spills. Quite a while ago, the industry went to using closed loop drilling systems. So basically, all the fluid flow with the drilling fluids is all in basically a closed loop system, which greatly minimizes any risks to the environment. And then having the well pads lined, which is in essence a regulatory requirement nowadays. So if there is a spill, it doesn't seep into the ground. It can be contained at the surface. Another issue, which I'm sure many of you are familiar with, would be the potential for stray gas or methane migration, where methane leaks away from the well, can get into water supplies. And this was an issue, especially 14, 15 years ago, when not as much was known about the subsurface geology. Some of the shallow methane especially caught the industry off guard. The wells weren't drilled to contain it. Since 2011, the state's regulations have changed so that you do have to put additional casing and cement into the ground to seal off any potential, especially shallow gas. So it wasn't necessarily methane from the Marcellus that was leaking as much as it was shallow gas that the industry just didn't account for in their well construction. We do see, pre-drilling water quality testing is pretty much the norm nowadays. Otherwise, the industry, if they don't do that, they'll be liable for any, environmental issues there. So overall, the well regulations, well construction regulations have improved greatly in the state. And part of that is also doing annual well integrity testing, making sure the wells aren't leaking, which can be done basically by, pressure testing or other methods. So again, there's certainly challenges. I'm not trying to minimize anything, but I'm also trying to say, there are things we can do to minimize those risks and minimize the potential environmental impacts, because, whether we want to admit it or not, this is an energy source that most of us use on a daily basis. We're in an energy hungry world, and, we do have to find cleaner sources of energy and minimize, the associated, potential environmental impacts. I mentioned well integrity. What I mean by that is making sure that the well does not have any leaks. So, basically what that entails, if you look on the right-hand side of the slide here, is that, whenever you put steel casing into the ground, the steel pipe that's designed to seal off the part of the earth that it's installed into, you also have a layer of specially designed cement around the outside of that steel casing, so that in theory, nothing should be able to leak up around it. Now, is this perfect? No. Can leaks happen even under the best circumstances? Potentially, yes. But this is the state-of-the-art technology that's been developed to try to extract the energy while minimizing the potential for methane to leak away from the well or for other fluids to leak up through the well. So again, when we think about methane migration, it's not necessarily associated with hydraulic fracturing. That's sort of a common, I'll say, misconception out there. It's really how the well's constructed. And there's a couple of close-ups in the middle of this slide that basically show, if there are fractures in the cement, if it didn't set up properly, it could have been a bad batch of cement. It just might not have been meant for that environment. there's a whole host of factors why cement might not get placed properly or set up properly. And in those cases, you can have a poor seal at the end of the day. And that's where, methane doesn't require a very large fracture. It can, these molecules are small. They can sneak through a very small opening and find they'll take the path of least resistance. And oftentimes that ends up being a nearby private well. We've done some work looking at well integrity issues as it relates to methane migration. And this was not that long ago. I looked at it, and out of the roughly 12,500 wells that had been drilled, approximately 40 of those shale gas wells had some sort of stray gas issue. So that checks out to be about a 0.3 rate of known stray gas leakage, and on the order of 200 private wells have been impacted as a result of that. So it just kind of gives you a sense that, it's not common, but when it does happen, obviously, it's a very big deal to, the folks whose wells were impacted, and as well as the industry, because, they don't want to be responsible for impacting somebody's, drinking water source. So that's, on the well construction side, those are some of the issues and some of the potential approaches to minimize those issues. With respect to hydraulic fracturing, we've got, fluid management's always going to be a challenge, whether it's fresh water or the produced water. What we're seeing the industry do is pipe fresh water to sites rather than truck it to sites, takes trucks off the roads, reduces the potential for issues with truck traffic, takes them off, rural roads, reduces carbon footprint of the industry. As far as the fracturing additives, there are less toxic, I'll say, or greener completions that can be used out there. And so, the industry does largely try to minimize the use of those additives. For one, they cost money, so they have an economic incentive to not reuse or overuse those additives. So, there are reasons why they want to use less chemicals, just beyond, the environmental side of it. There's an economic side of this as well. Diesel emissions, similar to drilling, you can see in this picture, there's a whole fleet of pumping trucks there and other equipment, all using diesel. You are starting to see, again, the industry switch over to using natural gas. They can use field gas, using their own fuel they're producing to power the equipment they're using to produce more. So again, that, is natural gas obviously can be a potent greenhouse gas, but diesel, has its own set of issues with particulate matter and things of that sort. As far as, surface spills and blowouts, we've really, because regulations improved back in the early 2010s, there are multiple barrier pressures there. So you're not seeing, there were a handful of incidents where there's, control of the well was lost. You had fracturing fluids, produced fluids, basically spraying in an uncontained manner until the well could be brought under control. Again, there's always that risk, but that risk has been greatly minimized because of multiple pressure barriers or blowout preventers, BOPs. And then, there's always going to be the public concern, right? And so, there has been efforts for greater transparency, both through NGOs, DEP, academia, to, get a hold of this data, put it out there in the public so people can, look at it themselves. So researchers can use it to evaluate how the industry's operating, and things of that sort. So when we think about, the water that's being used, as I mentioned before, and as we saw from some of the SRBC data, you're looking at, water use in excess of 10 million gallons per well. On some of the larger wells, it could be in excess of 20 million gallons. Most of the water is surface water. Much of the water is coming from larger sources of water, such as the Susquehanna River. While that might not, appease all, it does spread out the where the water is coming from, rather than taking it from small headwater streams or exceptional value trout water streams, things of that sort. So, and the Susquehanna River Basin Commission does do they tightly regulate where the withdrawals are coming from, and I think do a pretty good job of making sure that the water that is withdrawn is at a level that again minimizes the impacts to the health of that stream. The industry has gone, rather than using fresh water, again they're trying to maximize recycling of the produced fluids. So that's on the order of 90% recycling rate there. And, the amount of, or the relative percent of produced fluids being added to a particular frac are about 30%. So you might have 70% fresh water and 30% produced fluids. In some cases, that might be 80% produced fluids and 20% fresh water. So again, minimizing the amount of fresh water being used. Rather than trucking water, as I already mentioned, you're seeing more and more water pipelines being put in. So that takes the trucks off the road and all the host of issues there. And we also are seeing, innovations in water storage on the site. Rather than large surface impoundments, you're seeing smaller temporary tanks that can be moved once they're done and reused at the next site. So minimizing the earth disturbances there. When we think about water resource impacts, with groundwater, we already talked about methane migration and what's being done there. With surface water impacts, if you do have a spill at a site, the potential for it to run off into an adjoining stream again, there's always that risk. But if you have lined well pads, bermed well pads, and setback distances, again, you minimize that risk. Again, never removed, but minimized. And then one of the risks, especially in Western Pennsylvania, where you've got a lot of old historic drilling that goes back to Colonel Drake's wells. We've got several 100,000 old abandoned wells where we really don't have any records of where they are. There is potential for a new shale well to hydraulically communicate or basically allow gas or fluids to flow up through that abandoned well, because it acts as a conduit. Again, it's the path of least resistance. DEP has enacted some new regulations in the last few years that the industry has to do a better job of surveying within a 1,500-foot radius of a shale gas well, to see if there are any old wells that are unmapped that might represent such a hazard. And then with produced fluids management, again, we talked about the 4 pathways that those fluids can be, handled. We do see a lot of reuse. A lot of that's occurring in the field. Reusing in the field will, minimize the overall carbon footprint rather than trucking those fluids anywhere. And we're seeing more and more of those fluids being used in higher proportions compared to fresh water. One of the challenges is brine disposal capacity, where there aren't opportunities to reuse those fluids. We do have, as I'd mentioned, about 12 permitted disposal wells, all in Western Pennsylvania. A lot of these are in depleted gas fields, conventional gas fields where the gas is removed, but yet there's storage in the subsurface, and under the right conditions, you could use those fields to store natural gas, which we do. We have about 60 natural gas storage fields, or you could use them to dispose of brine fluids and basically repressurize the subsurface to the level that it was once pressurized up two. We don't have the geologically, we're a little bit limited on where subsurface disposal of brine can occur. But ideally you would locate it, away from populated areas. You need to find the right geologic characteristics. And again, that's why depleted conventional gas fields are a common approach to that. There is potential for induced seismicity, basically low level seismic events. Pennsylvania is not really a high risk place for that, just geologically speaking, although it could happen. Although nowadays there's seismic monitoring to pick up on if there are any slight seismic waves, you can shut down the field and make sure that it's not being caused by brine disposal. But these tend to be very controversial projects, as you could imagine. And, while the EPA will say that this is the safest way to dispose of these brines, the public might not exactly be buying that, and that's quite understandable. And that's where, educating ourselves about, the best possible ways to manage these fluids is, I think, an important part of that. And that's all I got for you. So just kind of a quick and fast overview. Probably left more questions than answers out there. And I'm more than happy to answer as many of them as I possibly can for you. So I appreciate the opportunity to be here with you.
Thanks, Dave. We'll entertain a few questions now. And if there's excess, because we're on a tight timeline, perhaps they can contact you directly through email. Would that be okay?
Absolutely.
So for those that are here, any questions for Dave? Right. We'll go from left to right. Right? Byron?
Just a quick one. In one of the slides, you mentioned about 8% of the recycled wastewater is to Virginia. Why isn't that reused around the Pennsylvania wells?
Well, if you think about where some of the development's occurring down in especially southwestern Pennsylvania, some of the same companies are drilling in Pennsylvania and right across the border in West Virginia. So they may just keep their fluids within their own company and transport them across the border to fracture one of their wells across the state border.
We'll go around. Andy?
Yeah, I had a question in regards the social costs. Your program was very industrial and I get an idea of how the industry works. But I read 3 weeks ago or so, 3 or 4 weeks ago, of some kind of a settlement on well pollution. And does your organization at Penn State keep track of the negatives, the incidents where wells are impacted? I'm thinking of the people who, before, when these wells were going in, said, geez, I sure hope it doesn't affect my well. It did affect some wells. It took 14 years to resolve that case. If I understand the case correctly, it took 14 years to resolve it. And they came up with a settlement where water will be provided free for 75 years and things like that, some monetary thing. But in the meanwhile, the industry denied having done anything to the wells, even though, so anyway, that type of thing. Do you keep track of that at Penn State?
I don't exactly keep a database. I mean, the DEP does have a violation database. So you can go through and track, where these kinds of incidents have occurred. It honestly, not all of it, because this is, oftentimes an agreement between a private agreement between a company and a landowner. These aren't always publicly announced situations. I'll say it that way. But you know, the case you're referencing to, and I believe you're referencing to Dimmick Township in Susquehanna County. Yeah, was certainly a protracted process there, and a situation I don't think really anybody would want to be in. And yeah, and that's why I try to emphasize, you know, the industry. There's certainly no shortage of, I guess you could say, you know, externalities, potential for externalities, where, you know, there's air pollution potential, water pollution potential, your drinking water could be impacted. So, you know, we can track these things. The state does track these things. And so there are databases you can go to, which I'd be happy to share the links with you.
And just one follow-up, originally, the formula that's used for the fracking, they called it a proprietary formulas, and they were proprietary. They were not in the public domain, because of, they call it the Halliburton loophole, that these things didn't have to be disclosed, which would make someone uncomfortable who's nearby. Has that changed at all?
Yes, it actually has. So now in Pennsylvania, the companies for each well have to disclose what chemicals they're using and provide the material safety data sheets to DEP. They can, in some cases, say certain chemicals are proprietary and not exactly disclose the specific, you know, chemistry of it, but do have to say what the purpose of the chemical is. Is it a friction reducer, a biocide, an iron control agent, things of that sort. So by regulation, the industry does have to, in a publicly available way, transmit what they are using. And so that's on fracfocus.org is the website, where basically it's a public registry. Again, some chemicals they may claim as confidential, so they don't have to specifically disclose them in the public, but they still do have to disclose them to DEP, so that if there were a need for an emergency response, they know what they're dealing with.
Yes, David, thank you for your presentation. It was very interesting, but it was hard to digest in such a short time. Would you have an information package that you could send us, that we could kind of study this at our leisure and to be getting more information on it?
Yeah, I know. Yeah, again, I know I had you drinking out of a fire hose there. Yeah, I mean, I'm more than happy to share the slides, and then, you know, if anybody has any particular questions, my email is right there, and I can address specific issues and point people in the right direction.
Thank you.
Absolutely. Thank you.
Two quick questions for you. One, from what I understand, Marcellus gas is considered a fossil fuel. Is that correct?
Yes, it is.
So what type of fossils existed that deep and that long ago?
Yeah. So if we were to transport ourselves back in time about 390 million years, we'd actually be somewhere near the Bahamas, and which sounds nice right now, and probably be under about 100 feet of water, and so we'd be in a shallow inland sea, and we'd be rained on by all of the dead fish and algae that were falling to the bottom of the ocean. And so basically all the organic material in there is really the sort of the source for the ultimate source for the hydrocarbons. You just need to add some heat, some pressure over the course of time, and it converts that organic material from that algae and other, you know, phytoplankton, things like that that are floating around in the sea to be converted into, you know, oil and natural gas.
So,
Thank you.
so it's basically organic material.
Yes. Correct.
Thank you.
Yep.
Okay, I have one more question. A while back, I read an article about how water-based fracking would be supplanted by using pressurized gas. Was that just a, you know, a thought, or is something coming down the pike that will eventually replace the need for water fracking?
Yeah, in certain places that can work. Basically, you know, you're pressurizing, in essence, liquefied petroleum gas. Think about, you know, in essence, propane. So you're sending pressurized propane down into the well instead of water. So, you know, there's some, as you might imagine, some a whole unique set of inherent risks associated with that. But the gas fracking technologies are out there. The problem is that gases, even liquid gases, are fairly compressible compared to water. So that's why water works so well, is it's virtually, you know, incompressible. So you don't have to, you know, put a lot of pressure on it to overcome the pressure loss because of its compressibility. And so it's simply the, you know, incompressibility of water that makes it so effective. But there are other technologies out there. They just are probably more expensive and less effective.
Thank you.
Aaron, you have
Yes.
2 questions.
Oh,
John
okay.
and Barbara.
Okay.
Don Hamilton.
Don? Okay, Barbara?
I have a question.
Sorry, I was
John?
on mute. I was on mute there. Sorry.
John?
Dave, I was wondering what kind of advances have been made in reducing methane emissions in this industry in the last 10 years.
Yeah. So yeah, that's a very active area for research right now. Some of my colleagues here are, you know, some of the leading researchers on doing what they call top down and bottom up air quality monitoring. So basically the bottom up would be having, you know, sensors on the ground that can pick up, you know, methane and other gases. The top down means you're in an airplane and can survey with special equipment just how much methane is in the air. And so what they're trying to do is try to have all the numbers add up. You know, you can take if you're in an airplane and you're looking down and you've got the right instrumentation, you can get a pretty good estimate of just how much methane is in the air. Measuring it on the field, down in the field on the ground, is a little tougher. Depends on which way the wind's blowing, and there's just a lot of factors there. But they've actually got the numbers to pretty much converge at this point. And if you look at shale gas wells in the Marcellus in particular, you know, the leakage rate is on the order of 0.1% or so. If you look at some of the older conventional wells, it's more like 10% in some cases. So, you know, several orders of magnitude greater leakage. So the EPA and DEP have their own estimates. So everybody's trying to get their estimates to make sense. What we're finding is when you have significant releases into the atmosphere, it's usually from one, or I'll just say several, larger emitters rather than 1,000 smaller emitters. So the good news is it's easier to fix one large fugitive emission, is what we call that, versus 1,000 smaller emissions. And so, yeah, so there's a lot of technology that's being deployed, and, you know, the regulations are also shifting that way to do a better job of detecting, well, for one, detecting the leaks, but also using equipment, the valves, actuators, and things like this in the pipelines and at the wellheads that aren't gas driven. Because that's where you just have some inherent emissions. Some of these things are, you know, they use the pressure of the gas to activate the valves, thus releasing some gas into the atmosphere. So they're getting away from that kind of technology. So to answer your question, yeah, there's a lot of research on finding the sources and fixing the sources, and actually, putting newer and better technologies out there in the field that, don't have leaks implicit in how they operate.
Thanks.
Yep.
Barbara?
Yes, I think I'm unmuted, am I?
Yep, I can hear you.
Okay, good. So does the Marcellus Center calculate the economic value to the industry of the exemptions? Because not only is the waste not handled as the toxic material that it is, it was made special in the 1980s, and that's why it can be hauled around without being tracked or manifested, etc. And then there's all the exemptions in the 2005 Energy Policy Act, plus all the oil and gas workers were removed from most of the OSHA requirements. So even not looking at the health impacts of all of the drilling with the chemicals, et cetera, et cetera, et cetera, just looking at the economic value to the industry of the exemptions, does the Marcellus Center look at that value? Calculate it?
Yeah. Honestly, I'm just a dumb geologist, so that would take somebody smarter than me to be able to estimate that. But I do hear what you're saying. So basically, oil and gas wastes are regulated as being residual wastes versus, as you note, hazardous or otherwise. Meaning that, those wastes can be taken to a residual waste landfill along with any other, commercially derived waste, in essence, things of that sort. So while I particularly don't track that, I would imagine there are, other researchers out there who do. And I don't know who they are off the top of my head, but I would be happy to try to find somebody who might be able to, or find some information that would address that particular issue.
If you could, and that would be really great to send back to the council.
Okay, I will do that.
Thank
Dave, we got to wrap it up. It's 8 o'clock, and we have a full agenda yet, but I want to thank you for your enlightening presentation. And I think there's as many questions as there are answers. So
All right. Well, thank you very much. I appreciate the opportunity. And again, I'll follow up with some answers, and feel free to reach out anytime.
well, thank you again.
All right. Penn State. Take care. Thank you.
All right, you too. Okay. Moving on to our agenda.
I'll move on.
Do I?